Hey, James, if you have any questions, feel free to ask. We got some time before class starts. Hey, John. I was just telling James, if you have any questions, you're welcome to ask them now. We've got about 6 or 7 minutes before class starts. So you're certainly welcome to anything about the past, syllabus, anything like that. So no questions is cool. I'm just sitting here organizing my class a little bit.
I got questions, but I literally just walked through the door from work, so I was logging on and whatnot. So
no problem, no rush.
I think my biggest thing with Gauss's law and pretty much everything we've done so far is like you get the equation, especially what we derived, but then when we do problems, we use it in different ways. Take example, we did the Q problem with the charge in the center,
Right.
and we integrated over each side of it, right? And then it all got, the summation of it ended up being 0. I think it was, if I remember right. But then you do a different problem. You're still using the same exact equation, but you use it in a different way. I saw that you had put something up on Canvas about up on Gauss law, so I haven't read that, and that might answer my question, but I figured I'd ask while I'm here.
Yeah, there might be a little misremembry, but the first one, when you were talking about there's just a point charge at the center, that was basically me taking and trying to show you, hey, here is a way one might have came up with the idea that Gauss's law is what it is. So what I did was I imagined just a point charge like sitting at the origin. And then I knew that the actual flux formula is the integral of E dot dA. But if I do it over a closed surface, one that clearly has an inside or outside, like, this McDonald's cup, because I've got a lid on it, it has a clear inside or outside. There's no way a molecule of T is going to get out here unless it goes through this plastic lid or through this plastic wall or through this plastic bottom. If I took the lid off, then it'd be ambiguous because I could go here and claim I'm inside. I could go here and claim I'm outside. So what I did was I used a sphere, which obviously is a closed surface, but I centered the sphere on the point charge Q because I knew, according to Coulomb's law, the electric field around that charge Q was Q over 4 pi epsilon naught times the square of the distance you are from the center of the point charge. Since the center of the point charge is at the origin, that R is just the same thing as we use like the spherical coordinate R, but more importantly, it's just a distance. And as long as that distance is a constant, you get two things. One, you get a sphere, and two, you get Coulomb's law gives a constant electric field. Because of that, then I knew E was a constant on the surface of that sphere of radius R, and E pointed, in fact, perpendicular to that surface. So if you imagine the sphere centered on the origin of the XYZ plane, if you took a spot on the x-axis, then right there on the x-axis on that sphere, the electric field would be pointing parallel to the x-axis. Whereas if you did it on the y-axis, the electric field would be pointing parallel to the y-axis. And if you did it on the negative y-axis, it'd be pointing that way. If you did it at 45 degrees between the x-axis and the y-axis, it'd be pointing radially outward. So you see everywhere, it literally is on the surface of a sphere pointing radially outward. Because of that, E dot dA is consistently just E times dA. But you're on a surface whose radius is r, so Coulomb's law says the electric field there is a constant because it can only depend on r, and you're on a constant r. So you can pull that E of r in front of the integral, and you just integrate dA over the surface of a sphere. That gave you the left-hand side is equal to E of r times 4 pi r squared. On the other side, if you look at it, you say, oh, well, the total charge enclosed is just that Q. So Q over epsilon naught turns out to be what the total flux is. So that was why I was doing it with that charge initially. And I don't recall ever getting zero. Now, when we did, for instance, a Gaussian, what I call a Gaussian pillbox, which is essentially a cylinder, which for once in my life, I do not happen to have a cylinder next to me, which I almost always have somewhere near to me, is some sort of cylinder. Well, the pencil's sort of a cylinder. I use it.
I think the cube was for, it wasn't actually a point charge. Now I think of it, I think it was a
if you did
field.
Cube, that's exactly right. Yeah. If you were talking about the cube I integrated over, that was okay. So that one was purely my attempt to show you exactly what a surface integral is and what it means to be doing a surface, or like I did last time, a line integral, which is an integral along some path or along some line. When I did the cube, I was just showing you, hey, here's a made up electric field. I just pulled it out of my rear end, just made it up. And here's a cube I just pulled out of my rear end and made it up. Let's evaluate the electric flux through that, through the surface of that cube. And if we get anything other than zero, then that was going to be sort of a failure on my behalf, because I was trying to create an electric field that wouldn't need a charge inside of that box to make it. If I did certain things, I could have forced the flux to come out to non-zero, in which case that would tell us, according to Gauss's law, that there was a charge enclosed. So yeah, that actual closed integral, surface integral of the flux basically turned out to be zero, specifically because I tried to make sure I didn't create an electric field that required a charge be inside it. If there was, in general, a charge inside of any closed container, then the flux has to be non-zero. In fact, the flux will be Q over epsilon naught. So maybe that's part of it. Now, I did put that up on my YouTube channel, and I think I called it, I think I called it a long, tedious, but useful surface integral. That's what it is on my YouTube channel. And then today I put up 2 more lengthy videos explaining, well, the first one was 38 minutes long. It was me solving just one problem with Gauss's law, but me explaining all the details that were going in. That's why it ended up being 38 minutes. I wanted it shorter. I was hoping it was going to be like 25, but it came out 38 minutes. And then the next one came out to be like 22 minutes, and that was supposed to be quicker. I'm going to put out, I got 2 or 3 more I'm working on, and they'll all be put up probably tonight and or tomorrow. And they're specifically about how to use Gauss's law. So by all means, what you're thinking, the problems you're having and what you're seeing, those are good thoughts, and they're good that you're coming up with them, and you're good that you have those questions. So by all means, check out the videos that I post on my YouTube channel, and hopefully that'll help you. In fact, on one of them, I called it a good first example of Gauss's law. And I gave you links down below in case you didn't understand some part that I start off with, which is those coordinate systems. I gave you some links to the coordinate system videos too. So hopefully that'll help you. Was it John or was it James I was talking to?
It was me.
Okay, thanks, James. All right, well, it is 5:23 now. Does anyone have any questions before we get cracking on the rest of this? Okay, so one thing I wanted to do is I've essentially talked to you about all of these stuff that's relevant from chapter 23. So 21 was Coulomb's law, and I showed you how to, one, do that with discrete charges. So when you have a number of point charges or a number of spherical charges, excuse me, it turns out when you have a number of spherical charges, the spherical charges act just like point charges, with all their charge at the very center of charge of the spherical charges. So that's why you can treat them like they're discrete as well. But I also showed you how to deal with continuous distributions of charges, for instance, like the infinitely long line of charge along the z-axis, say, and we were able to calculate some distance away from it what the electric field was. We were also able to do that for a ring of charge, and we were also able to use the ring of charge to do that for a circular surface of charge of finite width. But then we even considered letting the radius of that circular disk of charge go to infinity, and that gave us what Gauss's law had given us for the electric field near an infinitely large charged plate, which turned out to be just sigma over 2 epsilon naught. So we did all that stuff. Then in chapter 23, we did all that with Gauss's law, which the way we were using it was kind of odd. We were taking this Gauss's law, which is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And we were trying to extract the electric field, the E, out of the integrand of the left-hand side. And that's a neat trick that we can do, but it can only be done in very highly symmetric situations where everywhere on some closed surface, that's why the integral has a circle on top of it. It can only be done for Gauss's law on a closed surface that has a clear inside and outside. So as long as everywhere on that closed surface, the electric field is a constant, then that means the electric field can come out in front of that integral, and you're going to integrate just plain dA. And not only that, because the electric field is a constant on that surface, it turns out the electric field has to be, in fact, perpendicular to that surface where it's constant. And that happens to be parallel to dA. So the dot product automatically becomes just 1, and you end up integrating just E of R times the integral of dA. So you always get on the left-hand side some electric field times some area. So if that, for instance, that surface area, that closed surface you were integrating over was a sphere, then it'd be E times 4 pi r squared. But that's not the only way it can be used. It can also be used if there's, more than one surface. And for instance, one particular surface has that nice feature that the electric field is everywhere uniform. In other words, everywhere constant on that surface. So imagine, I guess this is innocuous enough. Actually, it might not be. So imagine this is a a cylindrical surface that actually has a glass lid, like it's got a glass bottom. So we're pretending like it's a closed surface. So if you happen to find a charge distribution that would create an electric field that's constant everywhere on the surface, then by definition, that would mean the electric field would point radially outward from the surface. But notice it doesn't have a Y component at all. It would point radially outward on this, which means E dot dA is going to give, for starters, E being a constant, and then the dot product is going to give whatever n hat vector points this way represents the direction of the electric field, happens to be the same, let's say, n hat vector that represents the surface area dA, so that the n hat dot n hat, which I ended up using as either rho hat or r hat, the cylindrical / polar coordinate version of a dot vector, hat vector. Those two dots to give you 1, and you end up with E being a constant over this whole surface that comes out in front of the integral, and then the integral of the surface, which is 2 pi r times h. Now, I haven't touched the top surface or bottom surface yet, so that's not technically a closed integral. That's just the integral of one of the sides. Now, the other option, like I told you, is if the electric field's not a constant on the surface, it better be perpendicular to the surface. So up here, we have dA vector that, since this is a flat surface here, the dA vector would have to point, say, in the positive k hat or z direction. And down here, the dA vector would have to point in the negative k hat or negative z direction. Okay. In that case, the integral of E dot dA gives you E that actually varies, because right here at the center, E is 0. So the electric field sort of is going to infinity. But as you get further and further out, it gets smaller and smaller to some E that's a function of R. So the E is actually varying all over the top of the surface, but the E is always pointing this way all over the top of the surface, which happens to be perpendicular to the dA. So when you go dA vector dotted with this vector, you're going to consistently, because the dot product is A times B times the cosine of theta, you're going to consistently get cosine of 90, which is 0. So you'll get 0 for the flux through this surface. Similarly, you'll get 0 through the flux through this surface, and everything comes out great. So that's the scenarios you have to be able to use Gauss's law in that way. It's still Gauss's law, so it's always true, and it always gives you something valid. It's just, if you're wanting to use it to solve for the electric field, which happens to be an integrand in an integral equation, then you have to have certain symmetries so that either the electric field is exactly parallel to dA and therefore constant on the surface that dA represents, or the electric field has to be perpendicular to dA, and so that the dot product goes to 0. So that's the only two choices. In this case, when I was talking about the electric field here, a clear example of that was the infinitely long wire of charge, because clearly, since it's infinitely long, right here there'd be a charge, say, of the infinitely long wire, and right here there'd be electric field that's pointing this way. And you might think, well, wait a second, there's a charge right up here that's going to make it have a component sort of down this way. But you'd say, wait a second, if I go to the diametrically opposed spot down here, there's another charge just like that one pointing up. So consistently, the component of the electric field up and down are always canceling out, leaving only a component of the electric field pointing this way. That's why these surfaces give me the non-zero part of Gauss's law for the left-hand side. These parts give me the 0. If I change and talk about an infinitely large surface like this going to infinity, I would still use the same surface, say this going all the way through and looking like that. But in this case, the electric field everywhere points this way, or this way from under the plate. And in this case, the E is constant on this plate. So the integral of E dot dA becomes E times the integral of dA times the negative k hat dotted with negative k hat, because the electric field would be pointing down here. So its direction is negative k hat, and the dA would point down here. So its direction is negative k hat. So you'd end up getting a constant electric field, E of what we would call Z, times just the surface area, which you could just call A. You don't need a formula for it. In other words, you can just say E times A for this bottom one. And then on the top one, you'd have an electric field pointing up. Again, remember, this is cut in half by the infinite surface. So the other one was below and this one's above. The electric field will be pointing up in the k-hat direction. Well, the dA would also be pointing up in the k-hat direction. And from symmetry, since it's an infinite plane, the electric field will have no y component or x component. It's always going to be z component. So I'm going to have E being a constant on the surface, E of z, that comes out in front of the integral, and I get the integral of dA k hat dot k hat, because both dA and E point in the positive k hat direction. So I just get E times A again. This part, I've got a vastly potentially changing electric field. The electric field could be very, very strong right next to the plate, and it could get weaker and weaker and weaker and weaker. And not only that, it's all pointing up above the plate, it's all pointing down below the plate. So as you integrate it around this surface, you're consistently getting an electric field that's changing. And that seems like everything's going to fall apart. But here's the good news. The electric field points in the k-hat direction above the plane and in the negative k-hat direction below the plane, whereas the dA vector everywhere points in the what we call rho hat. If we're talking about polar coordinates, rho hat or r hat, or cylindrical coordinates as well, you could call it r hat, which only has x and y components, no k component. So you're going to consistently get a 0 for the integral on this side above the plate and on this side too above the plate. So in that case, you end up getting EA plus EA, EA for the top and an EA for the bottom. Hopefully that helps you have a little bit more of a fundamental idea how we are making Gauss's law work. So that was chapter 22, and chapter 22 was like a couple of pages, and they really expect you to do it in a day. That's mainly because in chapter 23 we covered voltage, and voltage is sort of like potential energy, but just like when we got potential energy from a force, like we had F equals mg, we got potential energy equals mgh. Well, in this case, we went from F being a force to E being an electric field, which was basically the force divided by the charge. Now we're going to introduce a potential energy, which again is like in joules, it's just like the mgh. But we're going to introduce another version where, just like we did with the force, we're going to divide through by a Q. And that's exactly what the electric potential is. Notice the difference. I say the word electric potential, or I say potential. Any of those mean voltage. If I say electric potential energy, if I ever use the word energy, then we're talking about something that's measured in joules again. The difference being the electric potential, the voltage, the potential, they're all measured in joules per coulomb, which is defined to be the volt. So that was what we did basically with chapter 23. I ended up taking an integral out to a sphere of radius r from a distance infinitely far away, where reasonably we would expect the electric potential to be 0. And I did a line integral all the way in to some distance r away, and I got that V, the electric potential at that distance r, was just the charge Q of the spherical charge distribution, or even the point charge if you wanted to, divided by 4 pi epsilon naught times r, where r is the distance away, and it's a scalar quantity. Okay, so that's what we can use when we have a point particle, or if we have any spherically symmetric charge distribution, we can pretend like it's a point particle at its center and use that formula. If, however, we got a smattering of charges making up, say, a flat disk, then I'm going to have to break up those little charges into dQs, and each of those dQs is going to have a electric potential given by dQ over 4 pi epsilon naught r. But it's a scalar, so it's a lot easier to integrate. I don't have to deal with dot products and cross products and all that stuff. It's just a scalar. So that's what chapter 23 was about. And tonight we're basically going to go into chapter 24, but I wanted to make sure we rehash that. And also something I didn't cover, it's fairly trivial, but it's something that you need to know. So does anybody have any questions on that recap I just did? Anything in there confuse you? Anything in there help you? Also, one student stayed late last class and asked me for a different example of using an integral to calculate an electric field strength. And they gave me just anything other than what we've already seen. So I made up one, and I slowly went through it and tried to explain it and asked leading questions and stuff like that. So at the end of last Thursday's video, this previous Thursday's video, you'll see a pretty well worked out integral or integration of Coulomb's law to calculate the electric field near a half of a circle of charged of a charged half circle, basically. So if anybody wants to look towards the end of that video, you'll find that that's helpful there. I think it helped the student, and the main thing is if it helped one, maybe it'll help you as well. So if you are having any difficulties with that, by all means, check it out. So any questions before I jump on? All right. So one thing I definitely want to do is I want to remind you that there's this thing called electric dipole. We talked about it several times so far. The electric dipole you can sort of picture as a positive charge and a negative charge next to each other. The positive charge and the negative charge have exactly the same magnitude. So it could be, 38 microcoulombs and negative 38 microcoulombs. That would be fine. And if you multiply that magnitude of charge, 38 microcoulombs, in other words, the positive version, just multiply that by the separation between their two centers, you get something called the dipole moment, which has units of Coulomb meters. Okay. Now, if you also define that as a vector, then you have to define it in the opposite way a positive charge would go. So for instance, if I had the positive charge here and the negative charge here, the positive charge would actually want to get away from this guy and go that way. So if you actually call the vector pointing this way instead, or excuse me, this way instead, then that would be the actual correct direction for the dipole moment vector. And the dipole moment vector is called P, or it's given the symbol P. So all my little zombie soldiers are committing suicide. They're just falling off for some reason. Anyways, so if you have that, that's called an electric dipole moment. It's given the symbol P with, of course, it's a vector, so it's P. And then there's neat formulas for it. So that's the part that I'm wanting to cover. So I'm going to now share my screen with you. And the screen's going to be, of course, my good notes notebook in my iPad. And now that I have something to write on, I can actually show you what I'm talking about a little better than just explaining it. So what we can do, let Famata in here. What we can do is I can draw a point charge Q. And then I can draw another point charge, negative Q. And then I can say the length between the center of these 2 point charges, which obviously center of a point charge doesn't mean anything because it's a point charge. Let's call this L, the distance. Okay. Then we can define the dipole moment. And it's technically an electric dipole. Turns out there's a magnetic dipole that is defined entirely differently. So there's the electric dipole moment is defined to be P, and that P is equal to Q times, let's say, L with a vector symbol over it. Now, L, like I said, it points the opposite direction as the electric field would. So for instance, the electric field for this would is supposed to point in the direction in which a positive charge would want to go. So if I laid a positive charge dead center between those two charges, the electric field points to the right and would force the positive charge to move from the left charge to the right charge. But in fact, this vector right here is the L vector. In other words, it points from the negative charge to the positive charge. Okay. Because of that creation that we did, and that's the dipole. There turns out to be a quadrupole, an octopole, all those various poles, basically 2 to the n power poles, but the dipole moment's the one that we're using here. But if you go into double E electrical engineering, you might discover there's more. There's octopole and a quadrupole and all that stuff. But this is enough for right now. So by defining that P that way, we end up getting a lot of neat little things. So for instance, one of the things we find is that the torque, I don't know why I'm writing in red, the torque acting on a dipole moment in an electric field turns out to be P cross E. Okay, so if I take the vector P, which is represented by that QL that I just showed you, and I take the cross product of it with the electric field and where at the location of P, then that will give me the amount of torque that's being applied to the dipole moment. Because you can imagine, let me draw the electric fields as if they're uniform electric field. So here's a bunch of uniform electric field lines. And obviously the electric field is pointing in the upward direction, right? Let me now draw a dipole moment. This is going to be plus Q. And this is going to be minus Q. And this vector right here is going to be the L vector. Okay. Now, what you'd see is that this electric field is going to tend to cause this positive point charge to go this way, right? Electric fields point in the direction that a positive charge would want to go. Similarly, that electric field is going to compel this negative charge to go this way. So this is F on negative Q. And this one's the F on positive Q. And you can see that that tends to rotate. In fact, you can break these components up. You can say, okay, well, I've got this component right here is perpendicular to the rotation axis, or the lever arm, if you will. And this one's parallel to it right here. Let me do those in black. That'll make it a little clearer. So that one's actually contributing to the torque because it's tending to rotate the P in the direction of that arrow. Similarly, this vector has a component this way that's perpendicular to the lever arm, but it's also got a component this way that's parallel to the lever arm. You can see that the parallel components are going to cancel each other out, but these two perpendicular components are going to tend to rotate the dipole moment this way. Okay, that's a really bad looking thing I drew there, but it's going to tend to rotate it this way. And that formula gives it to you, torque is equal to P cross E. But that also tells you if those charges are just going to move on their own like that, then they must have some kind of potential energy that lowers when they do that. And in fact, that's another formula that you're supposed to know. And that is the potential energy U is equal to negative P dotted with the electric field. Okay, those are things I actually derived for you in chapter 21. They're covered a couple times in chapter 21. They do a dipole and calculate the electric field right over the middle. They also try to calculate the electric field right over, say, the positive charge, and you actually calculate what the force is if you put a charge there. But then by the end, they go ahead and define the dipole moment as that Q times L, and they work out that P cross E is the torque and negative P dot E is the potential energy. And remember, in general, and I said this rather quickly a second ago in my description of Gauss's law, whenever you have a dot product, that's exactly the same as the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, so we could also write this A, B cosine theta. And what that means is if this is a vector B and this is a vector A and they're tail to tail, then the smallest angle between them is the angle theta. And you can even see, obviously, if you made this into a right triangle, okay, you can see that this little bit right here is the B cosine theta. So the dot product is sort of taking A and multiplying it by the component of B that's parallel to it. So that's why we often use dot products to find components that are parallel. You could also make a right triangle using A, and you'd find it's A cosine theta times B. So in that case, you're thinking of it as it's finding the component of A that's parallel to B. Both are true. That's the main thing. Okay. So that's what dot products are. So you can obviously see U is negative P times E times the cosine of the angle between them. And obviously the vector in this case, we said pointed from the in the electric field case, this one right here, the vector pointed this way and the electric field pointed that way. That was the electric field and this was the P vector. So this would be the angle theta in terms of the dot product. So that's a rehash, if you will, of what a dipole moment does. Now, your book goes through and works out a neat little expression. And this is something that me as an instructor consider a chucker problem. Like I could give you a multiple choice problem where I ask you to calculate the electric potential a certain distance away from an electric dipole whose dipole moment is 84 coulomb meters or something, and I would consider that a complete chucker problem. But if you hadn't read that part of the book, it might not seem so. So here I am now introducing you to that part. Your book takes the time to work it out, so you can do that your own, or you can ask me and I'll work it out for you. But ultimately what you end up getting is P times the cosine of theta, all of that divided by 4 pi epsilon naught r squared is the electric potential for R being much, much greater than L. Okay, remember L's the length of the dipole. Now, what does this formula apply to? Well, what this formula applies to is if you take and say, okay, here is a charge right here of negative Q. And let's say right here is a charge of positive Q. Okay. And then we go way, way over here and say, this is a point at which we want to know the potential. V here is equal to question mark. Well, what we could do is we could calculate the electric potential due to being that distance, which I'll call R, away from the positive Q. And then I could calculate the electric potential due to being that far from the negative Q, and then add them up and I'd get exactly the right answer. what I'm showing you here is in the case of R being way, 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 way bigger than this distance L, which by the way, L, in case anybody's wondering, L is that distance. Okay. But if you take this and say, make a right triangle out of the long one whose length I didn't put, what you get is you realize this little bit right here is the extra distance that negative Q is from the point than R is, because obviously this is a line and perpendicular to it gives you another R. So both of those are R. And it turns out then under this circumstance, this is the angle theta that they're talking about. Okay. So that angle being theta is basically the theta that goes into the formula. Okay. So that's supposed to be a chucker problem. If someone asks you, you know, and what is the idea of R being infinitely large or something like that? In physics, R much, much greater than L implies L is, as a bare minimum, greater than 10R. Okay. In other words, L has to be at least 10 times bigger to come anywhere close, but really we prefer, you know, 100R, 100R or even 1000R would be better. So that's when we use things like R much greater than L. That's what we mean in physics by that. So that's the last of the dipole stuff that I didn't really talk about in chapter 23. But like I said, you do want to know it. And in fact, dipoles are really relevant for chemical engineers, for instance, and other people that work with molecules, because molecules tend to become polarized. For instance, water molecule has one side that is infinitely, or not infinitely, but a lot stronger at holding the electrons than the other side of the molecule. So the electrons act like a negative part of a dipole, and the other side, which is positive, act like the positive part of a dipole. So often at the microscopic level, you can treat a water molecule as if it's just a dipole. Go ahead, Michael. You have a question?
Yeah, so you said R is much, much greater than L, but then how is L greater than 10 times R?
Oh, yeah, thank you. That's a nice catch. R is much, yeah, I wrote that backwards. I'm glad somebody was paying attention, because yeah, that's kind of crackheaded of me. Anyways, let me rephrase that again. So what I mean is thank you for doing that. Let's say R is at least as big as 10 times L. Sorry, I wrote it, but we would prefer 100 L or even 1000 L. Thank you. That's actually something I hadn't prepped to do. And obviously when I'm thinking on my feet, it didn't prep. I obviously got everything backwards, but yeah, you're right. The L has to be really small. That means the dipole, at least from the standpoint of the person way out there where I want to know V, it just looks like a charge to us. It looks like a point charge, but in fact, it's a little different than a point charge, because it's actually a point charge and the opposite of that point charge. So it's almost like a half a charge, but it's not even that. So the way we end up dealing with it is with these neat little formulas. So yeah, thanks for catching me on that, because that would have been bad in the notes existing that way. So thank you. Anybody else have a question? And thanks for raising your hand on that too. Y'all are welcome to speak out. If it gets too loud where I'm finding that people are running roughshod over the rules or something like that, then I'll tell people, okay, let's start raising our hands. But until then, you're welcome to just speak up. I appreciate your kindness and politeness of doing a hand thing, but I would hate to miss you asking a question because I didn't happen to look at the screen at the right time. Okay. Thanks, guys, for that. Again, I use the phrase guys. That's built in me. It doesn't have any gender, so I apologize if that's aggravating too. All right, now that I have all that, the other thing I didn't discuss, I discussed it a little bit, but there happens to be a really convenient unit of energy that we can use when we're dealing with, for instance, the dipole moment of a water molecule. Okay. It turns out there's a unit of energy which we can figure out, because what we discovered was, first off, we said delta V, which is always, remember that capital delta, that triangle that you see, that's the Greek letter delta, and that's the capital version of it. Whenever you see that in a science, that definitely means final minus initial of whatever symbol came after it. In this case, this became the negative integral of E dot dl, and that is from the initial spot to the final spot, period. No ifs, ands, or buts about it. This is a function that we use quite regularly. And I reminded everybody last time that technically speaking, this is a path or line integral. It's not just an integral. What do we mean by that? Well, we mean the same thing as when I told you guys, hey, this is a surface integral. That means the integrand, in this case, E and DL, have to be evaluated on an actual line that you're actually following. Now, the vast majority of the time in using this function, that's not going to play a role at all. You're going to accidentally do it right anyway. Okay. But there is a time where it can become a pain. So you've got to pay close attention and try to do that. So what I always do is I try to draw a line connecting the end point and the final point, assuming I'm going down that. And then if that's in the XY plane, you can make up, for instance, y equals, f of x. So if you're taking, for instance, a parabolic path, it's y equals x squared. So dy is equal to 2x dx. So if you have a dy in there, you can replace that with 2x dx and then integrate whatever e is, and you'll have satisfied the condition of that being a line integral or a path integral. The other thing that I told you is you must choose either the limits of integration or the differential line element to show direction that you're integrating. Once you do that, the other just points in the direction of increasing coordinate. So if I was integrating, for instance, along a line, let's say r equals, well, let's just say a line from the origin out to x equals 1 million or something like that. Okay. If I'm going to integrate from x equals 1 million into the origin, then I can either write dl. I'll even write this down here so it'll make some sense. Let's say from 10 to the 6 meters, comma 0 to 0, comma 0. Okay. I can say DL is equal to negative dx I hat. And you can see, since I'm actually going along the x-axis, I've actually chosen the DL to indicate my direction of integration. So then the initial value would actually be 0, and the final value would be x equals 10 to the 6th. That's what I mean. In reality, we were actually going from 10 to the 6th to 0, but I had to put it in the positive coordinate direction because I'd already used the negative on the DL to decide which direction we're going. Any questions on that? We're getting ready to use it again because in chapter 24, we're going over capacitors. Let me see if there's anything else I wanted to make sure I pointed out to you guys before we move on to, oops, I don't know how that happened. I'm going to kill that. Ooh, now I know how. Okay. I'm trying to see if there's anything else really that matters. You will see this week in lab, we're doing electric fields. Okay. So that's something that's kind of important. And what I will say about that is, if you imagine, for instance, so I've flipped my page now. If you imagine, for instance, that there's a positive charge, let's say right here is a positive charge. And let's say right here is a negative charge. Okay. Well, from Coulomb's law, we know that E is equal to Q over 4 pi epsilon naught R squared, right? And you can see that the electric field is going to be a constant at any distance R from a charge, right? Well, if you can find all the places where the electric field is a constant, then you can sort of draw the electric field. Well, if the electric field is not constant, then that's going to cause charges to move from one spot to another, i.e. from the high voltage to the low voltage if it's a positive charge, or from the low voltage to the high voltage if it's a negative charge. So we can also use voltage, which, by the way, is Q over 4 pi epsilon naught R. We can say, well, voltage depends only on R. So if I imagine the positive charge being all by itself, then I would imagine this right here, that was supposed to be red, fool. I would imagine this right here being an equal potential surface. In other words, I would feel exactly the same force at any part on this circle as I do on any other part. Well, I did till I moved it. Okay. So that's what we call an equipotential. Again, I'm ignoring what the negative charge is doing, but I can do another one, in fact, and I can say that's another equipotential surface. Similarly, I can forget about the positive charge for a little while, and I can say, well, here's the equipotential surface for the negative charge. Here's another equipotential surface for the negative charge. Here's another equipotential surface for the negative charge. Here's another equipotential surface for the positive charge. Here's another. Here's another. and here's another dead center between them. All of those are places where the voltage is a constant. So for instance, you might say this line corresponds to V equals 1.5 volts. This line corresponds to V equals 0.5 volts. Maybe this one corresponds to V equals 2.5 volts. And this one would be V equals 3 volts. This one could be V equals 4.0 volts. Then this guy could be V equals 5.0 volts. This could be V equals 6.0 volts. This could be V equals 8.0, or excuse me, 8 point, actually I have to go the other way. It would have gotten smaller, so on and so forth. And V is equal to 9.0 volts. Those are some ideas. Now, in reality, they would actually have to be backwards. I ended up forgetting that I drew the left side positive and the right side negative. So really, those numbers should be reversed. In fact, I'm probably going to do that because I'm OCD. So, and I'd hate to have you guys look at this later and just think, oh crap, that's wrong, or really get confused about it. So instead, I'm going to say this one is 9.5 volts. This is 9.0 volts. This is 8.5 volts. This is 7.5 volts. This one right here, put it back in red, goes up like this and goes up like that. This one right here is going to be 7.0 volts. This one's going to be 6.0 volts. This one's going to be let's say 5.0 volts, and let this one be 3.0 volts, and let this one be 1.0 volts. Okay, that would be much more realistic. Those are called lines of equipotential. Now, we occasionally get students that have been in the military, and if it was the Marine Corps or the Army, that can come in super handy. I've heard there are branches, of course, in the Navy as well as the Air Force and even the Coast Guard that would know this. But if you've ever had to look at a topo map, these red lines are like the circles and that you'd find on a topo map. In other words, each one of those red lines represents a height above, say, sea level. So the red lines are in fact horizontal. If you tried to draw this as a topographical map, what you would see is you would have a point right here. Actually, let's not use that. Let's use blue. I'd have a point right here, excuse me, right here, which corresponds to the highest point. And then I'd have a point right here, which corresponds to the lowest point. Okay. And what those lines are would be something along the lines of, let's say, this, and then this, and then this, and then this would be one of these. And we got one a little closer to the next one, so that would be this. And we did 1, 2, 3, 4. So I'm going to do 4 first. And then the fifth one is the one that went all the way. And I had 1, 2, 3, 4 in between here. So that would be what those red lines look like from the side, as if it were a topo map. And in fact, the shape that you can infer from it would be, I'm going to use green so it'll look like mountains or something. You would infer that the shape goes something like this. Okay. Now, if you find the line that'll get you down the hill quickest, that is the direction of the electric field. So if you look, say, right here, look how close those lines are together. And notice that line is in fact perpendicular to all three of them. So it turns out the electric field is always perpendicular to the equipotential lines. Okay, so these red lines is what you'll actually be mapping in your lab. You're literally going to take a galvanometer, which is a thing that reads microamps, and you're going to put one terminal of the micrometer, or excuse me, of the galvanometer down on a piece of carbon paper, and then you're going to click on all the different spots on the corner on the carbon paper that give you a current of 0. Because if the current is 0, that means the voltage is the same. Once you've done one whole line, sort of like one of the lines I've drawn around the positive thing, then you stop and connect, or not really connect, but try to draw a smooth line through all your points that you did with that one. Then you move that one that you left sitting still the whole time, you move that and put it on another part of the graph paper, of the carbon paper. And then you find all the places that give you 0 current relative to that. That'll make a second red line. And you keep doing that until you get, about 7 or 8 lines in between your shapes. And you then have the topo map basically. And that allows you, after all that allows you to go in and create an actual electric field. So right here, what I'm imagining is, going back to my red, what I'm imagining is, let's use red for the green, green for the electric field. So I'm imagining this is perpendicular to, and by the way, all metals are equipotential surfaces. So you can pretend like this point charge is really a piece of metal, because in the lab it will literally be a piece of metal. So I'll go perpendicular to it, I'll go perpendicular to this line, I'll go perpendicular to this line, 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 and I'm trying to pretend like they're all perfectly perpendicular. Obviously I missed a little bit, but you get what I'm saying. And you also know that a positive charge wants to travel on its own in the direction of the electric field. So we know in this diagram, since the left-hand side is positive, that means the electric field must point to the right. Okay. Now, if I start here, I again have to go perpendicular. Then I get here, I have to go perpendicular. And then I get here, I have to go perpendicular. And then I get here, I have to go perpendicular, and then 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 perpendicular. So now I can say, my electric field line turned out to be perpendicular like that. Notice, because the left-hand side was the higher voltage, that'll be literally connected to the red on the power supply, in other words, and the negative one will be connected to the black. So I could do this again. All I got to do is make sure it starts off perpendicular to that surface, and goes perpendicular to each of these surfaces. And I now have an exact representation of the electric field. So on and so forth. So that's what you're doing for lab tomorrow. Is you're going to, or tonight I should say, is you're going to find lines of equal potential, and then you're going to use those to define the electric field lines. And that's like the first time you can actually see that these electric field lines that were conjured up just because we didn't like Coulomb's law the way it was. It turns out the electric field lines actually exist and the electric fields exist. Any questions on that? All right, so now that I've sort of covered all that sort of stuff, and again, we got the electron volt. Remember I said that delta V is equal to V final minus V initial, which equals the negative integral of E dot dl. And in fact, what it started off was work is equal to the negative change in potential energy, which is just plain U, right? And that meant that it was equal to the negative of the integral of F dot dl, because that was a line integral too, by the way, last semester. But anyways, that's F dot dl is the work. So if we then said, well, let's take the work and divide it by the charge that's having the force acting on it, that would be the same thing as taking the potential energy and dividing it by the charge that experiences that potential energy. And then that would be the same, of course, as the negative integral of F over Q dotted with DL. And we know that F over Q, does anybody want to tell me what F over Q is?
E.
Yes, it's the electric field. I don't know why I wrote a G there. Exactly. In fact, we said it was a limit, blah, 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 but that is the electric field. Okay. So what we see is the potential energy, delta U, has units of joules. The Q has units of coulombs. Therefore, the delta V, which is really the work divided by Q, actually has to have units of 1 joule per coulomb, which is defined to be 1 volt. Okay, so that's what a volt is. Now, if because of this, we know that because of this and the definition, for instance, of electric field and that sort of thing, we know that delta U can be equal to the charge times delta V. Okay, this is an expression that's important. It's an expression that we use, just like this unit is something that we use, and this right here is all something that we use. Those are all very important. But this last one that I just drew gives us a neat idea. Let's say, how much energy will a proton get by moving from, that should be, I hate when I hold the pistol there so long, by moving from V equals, let's say 10.0 volts to V equals 9.0 volts. Okay. So when I do that, it turns out that delta U is going to equal to 1.602 times 10 to the negative 19th coulombs. Anybody know why I use that figure?
Proton charge.
Yes, the positive is the proton charge. If I put a negative on it, it's the electron charge. And that this formula, by the way, this delta U equals Q delta V, that's one of the times where the negative on the charge being put in can absolutely be helpful. Remember, delta V is final minus initial. So I'm going to say that the final voltage, it went from V equals 10 to V equals 9. So the final voltage would be 9.0 volts minus 10.0 volts. And that's obviously equal to negative 1.0 volts. So I'll get negative 1.602 times 10 to the negative 19th. Remember, a volt is a joule per coulomb. So that's actually joules. And in fact, that is the same thing as -1 electron volt. Notice that E is exactly the symbol we use for the charge of the electron. And notice the V is exactly the symbol we use for voltage. But what we've done now is found a new unit of energy that is more appropriate for atomic physics, molecular physics, where you're dealing with energies on the order of an electron's charge times a regular voltage. Okay. So the potential energy actually went down for the proton because it went from 10 volts, which it didn't like, to 9 volts, which it liked moderately better. So we got a change in potential energy that was negative. And that's exactly what we expect, because that's exactly, remember, potential energy decreases on its own if nature will let it. So if you stuck a proton at a 10 voltage site, a 10 volt site, and it could, because nothing was holding it still, it could reach a 9 volt site, then it's going to go from the 10 volt site to the 9 volt site and be more comfortable. So its potential energy will have dropped, which is why we got the negative. So this is a new version of energy, a new unit of energy. And what we say is 1 electron volt is defined to be 1.602 times 10 to the negative 19th joules. Okay, so that's just another figure that you need to keep in mind. And a lot of times it's easy. Like I went to Dock in the Box in the Kitty Hawk area the other day, and they had to do an x-ray on my back because I've got a long history of back injuries, but I just suck it up and do it anyways. I was having a real bad back pain, so they went ahead and ran a x-ray of it. Well, I always, as a physicist, always look for numbers and quantities and stuff like that that are relevant. Plus I studied at a place where they used to have a master's in basically biophysics. So we had a lot of seminars on x-rays and radiation treatment and stuff like that. And I noticed that the energy on the x-ray machine was 25 kilovolts. So I knew immediately that if that was being used to, let's say, treat someone's cancer by bombarding their tumor with with electrons, which is a potential treatment they use protons. You've probably been seeing commercials from Hampton University on that. They use proton therapy. They use electron therapy. They use straight gamma ray therapy, which would be just photons. But I know for a fact that if you put a proton in that and use it to accelerate the proton, it would actually have an energy of 25 kilo electron volts. And that's just the beauty of the electron volt, is you just, you don't even have to take into account the charge. You just put electron volt as the unit, and then If it happens to be a kilovolt, then you make it a kilo electron volt. So it really is quite easy and quite nice to be able to make use of that. So any questions on that stuff, which really finished up chapter 23 in its entirety? You should easily be able to get all the chapter 23 homework related stuff done. I moved the dates recently, and I think you still have until Sunday to do chapter 23. I think chapter 22 was due maybe Sunday. But anyways, we're now going into chapter 24, and chapter 24 is called Capacitance, Dielectrics, and Electric Energy Storage. So that's where we're going next. So chapter 24. Which, as I said, was capacitance, dielectrics. Now, oddly enough, I took this course, and only a couple of years later did I realize all this time they keep talking about dielectrics. That's sort of a fancy word for non-conductor. So if you find an insulator or something that's not very conductive, you can also call it a dielectric, and everybody will think you're a lot smarter. Electric energy source. Okay, so that's what the chapter is called. And the main reason I wanted to put that to you is I want you to understand what what capacitance and all that stuff was. So let me share my screen real quick. I want to stop sharing the screen that I am currently, and I'm going to share another screen that happens to be, let's do this one, which is actually your books opening chapter, but that's not really what I wanted. I want to change this one. Are y'all now seeing a Google array of images? You should be. Okay, so these things are capacitors. A reference, like for size, that might be half the length of my thumb from there to there. So they're very, very small. These are not like ones that you'll find inside of your air conditioning unit or your heating unit that you have outside. And in fact, I've been fortunate enough that just about every time anything I have electronic breaks, I can open it up and almost always find a capacitor, which notice it has that fancy little Mercedes symbol up there. That breaks right there, and those things pop up, and you see little triangles stuck up. Or sometimes you'll see they're so bad that the whole thing's swelled up. A lot of times when something electronics goes bad, it's a capacitor that died. So for instance, when I was before 9/11, I got a really wonderful computer engineering, software engineering job for an awesome company. And I immediately started spending money because I was making a ton of money. I bought like a $7,000 TV. HD TV had just come out, and this was the biggest and the best. So I literally paid like $7,000 for a brand new HD TV and bought a new living room suit and all this stuff. Well, roll ahead about 7 years, and 9/11's come along. I lost that job. I was currently teaching high school for a semester in between doing engineering work. So I was teaching high school, had no money. My daughters went in, tried to play on the TV to use their video game, and they hit the button and it tried to come on, and I just started, and it just died. I called a repairman. He was going to charge me $175 to drive there. And then it would be $75 an hour plus parts. And I was like, God, that sucks. That's a lot of money. I said, how about if I bring it up there to you? He said, well, it's still going to be a $75 fee for me just to look at it, plus $75 an hour. I was like, okay, well, let me just take a chance. So I unplugged the TV, which is the first thing you should always do, but be advised, but strictly or almost always strictly because of these things, capacitors, that is not necessarily enough to protect you from being killed. Okay. So I opened this TV up, and it's got all these warnings warning radiation, warning high voltage, blah, blah. And they're right. There really are things to be warned about. But lo and behold, I looked in and I saw a capacitor that looked just like this one right here. Not only that did it look just like this one right here, well, it actually had two legs coming out of the same side instead of one out of both sides. But I don't see a better match to it. It's also sort of looks like this one, but it had the dark blue instead of the light blue. Yeah, I don't see one like it. But anyways, I saw the capacitor sitting there, and sure enough, that little Mercedes symbol had popped up. And I just happened to look in my toolbox that I had, and I had exactly that capacitor, the same temperature rating, the same power rating, and the exact same capacitance. So I cut the wire out of it. First, I made sure I grounded it. So I took the two edges, the two wires sticking out of the bottom of the capacitor, and I connected one of them to a ground wire, basically a wire that you can stick into that little half moon looking mouth of a receptacle. That's actually ground. So I stuck it to that, and then I touched the other one to it too. That way I knew at least that the capacitor was discharged. And then I cut the capacitor loose and then resoldered my capacitor right in place. Now, never mind the fact that I wasn't paying attention and actually took my screwdriver and it touched something along with one of the aluminum heat sinks and instantaneously got welded to the heat sink. My flathead screwdriver did, which is why I'm warning you that just because you unplug it does not mean you're safe. That was literally enough that it melted the aluminum, which doesn't have a high heat required to melt it, but still it's high. And it melted it enough for my screwdriver to get stuck to it. So that was a huge voltage, and it probably was just due to some capacitor that was still charged. Luckily, I didn't die. The TV worked for another 10 years. So I've had similar things with my pool pump. A capacitor went out with my pool salinator. In other words, I got a salt device that creates chlorine out of salt. That went out last year, and that was going to cost me several $100. And I looked, and it had a capacitor that was clearly blown. I ordered the capacitor. I think it cost me $8.48, and I put a new one in, and it worked fine. That happened to my HVAC unit, and I ended up buying one that looked like those big silver can ones I just showed you, and that was all I needed to fix my HVAC unit. Well, 3 years later, it finally died, and I had to replace it for real. But a lot of times you'll just luck out. Just be very careful. Make sure you ground everything that you're getting anywhere near and stuff like that. But sometimes you can look out and find a little fix like that. So let's go now to do an actual physics problem relating these capacitance things. So I've got like 5 minutes left of the class. I've told a lot of neat stories. So as an old person, I feel like I had a really great day. For some reason, my iPad's not even okay. I've had a really great day from an old person standpoint because I've told a lot of stories now. But it turns out that we can define a quantity, capacitance, as the amount of charge something holds for a given voltage V. This is capacitance. And it turns out there's sort of, in some sense, there's three major things that are relevant to circuits. Resistance, which y'all learned about with Ohm's law. Of course, there's obviously voltage and current, but you're talking about components in it. Capacitance is another thing. Resistance is another thing, which I already mentioned. And there ultimately turns out to be something called inductance or self-inductance. Okay. All three of those play critical roles and mess with timing of circuits and so on and so forth. This is the capacitance that we're talking about now. And the units for capacitance, I think you can see, is 1 coulomb per volt, which we actually define as 1 farad. And of course, that's also written just 1F, but it's much more typical to find capacitors on the order of microfarads, nanofarads, or even picofarads, because a single farad literally holds a coulomb of charge. And I told you guys coulombs are buttloads of charges. It's not abnormal for a lightning strike to have a few hundred coulombs of charge come through it. So a coulomb is a big thing. In fact, if you ever find a 1 farad capacitor that's either not hooked up in a circuit and does not have the 2 terminals connected to one another, then stay away from it, because it's probably accumulated enough charge that it could hurt you really badly, if not kill you. Okay. Well, how do we do with this? What do we do to make this capacitance thing a capacitance thing? Well, we need to understand how to calculate capacitance. So I'm going to show you that. We're going to start off with a parallel plate capacitor. The parallel plate capacitor basically looks like this. I'm going to change this color to black. I'm down a couple minutes here. A parallel plate capacitor has a plate positive and a negative plate, and they're right next to each other, like so. And they have a surface charge density sigma, and let's say an area A. And this one, of course, would have a surface charge density. This one would be a negative sigma. This one would be a positive sigma, but it also have an area A, and it had a separation distance D, like that. Okay. What we discovered the other day is that the electric field between the plates, E, equals sigma over epsilon naught. Remember, it was sigma over 2 epsilon naught for the positive plate. And then for the negative plate, it was sigma over 2 epsilon naught, but they pointed in the same way, in the same direction. So in that case, it became sigma over epsilon naught. What I'm going to do is create a nice little blue coordinate system. And that's going to be my y-axis. And this is going to be my x-axis. And that means this distance right here is D. And in order for me to find the capacitance, I need the charge divided by the voltage. So I got to find the voltage. So what I'm going to do is I'm going to calculate delta V, which is V final minus V initial, which is equal to the negative integral of E dot DL. Okay. I'm going to choose a path from, let's say, from here to here. That's the path I'm going to choose. And the reason I'm doing that is then the final voltage will be higher than the initial voltage. So I'll actually get a positive value. So the way I do that is I recognize that the electric field is in fact pointing in the I hat direction. So I'm going to say that sigma over epsilon naught I hat, that's the direction of the electric field. I'm going to dot product that with DL, and I'm going to let my limits of integration dictate the direction I'm going. Therefore, my DL is just going to point in the positive coordinate direction. So my DL is in fact going to be DX I hat. So that forces me to choose me choosing X equals D for the initial spot and X equals 0 for the final. That's where I chose my direction. Obviously, you get sigma over epsilon naught is a constant, so I'll pull that out in front. And I get the integral of dx from D to 0 times I hat dot I hat, which we now know pretty well is just 1. So I end up getting, don't forget the negative I had. I wrote it here, but I didn't write it here. So I'll put that there again. Now I've got sigma, negative sigma over epsilon naught. The integral of dx is just x. And I got to evaluate it at 0 first. That'd be 0 minus d. Like that. So in fact, what I get is sigma D over epsilon naught is the actual voltage. That also tells you that the units of the electric field can be thought of as volts per meter, which is a lot easier. So now I can say the capacitance, which is Q over V, that capacitance, in fact, is going to be sigma A over sigma D over epsilon naught. That's bottom is the voltage. The top is just the formula to find the actual areas. For area was the whole capacitor. That means my sigmas cancel out as they always should. You should only have geometric terms in your capacitance. So what I've now discovered is that the capacitance for a parallel plate capacitor, C, is equal to, in fact, epsilon 0 times the area divided by D. And that's it. Time's up for class. And I've done one derivation. You can see there's formulas for capacitors in parallel and capacitors in series. I will cover those and do basically most of the examples from chapter 24 I'll do next time. But I think you've got enough to get started here. You could probably even tackle the series and parallel capacitors just by reading the book. But let me know whatever you need. Give me a holler, send me an email. The actual test 1 will be up today or tonight. I think it's already is. And the practice test will disappear at the same time as the actual online test 1. And that should be Tuesday night at 11:59 p.m. So have a good one, everybody. I'll wait for the last person to leave and then I'll leave. Anyone have any questions? Julia, did you have a question? All right, looks like everybody's done. Y'all have a good evening. Bye-bye.